Hi everyone, my name is Sam. I'm a third-year computer science student at the U of O, and today I'll be talking about the research I did on interpolating sparse indoor temperature data that varies in space and time. Joseph McLaughlin, Professor Young in the computer science department, and Professor Rockcastle in the architecture department had built a parasitic data collection process based on the idea of mounting additional light and temperature sensors to devices already moving around indoors. Mobile sensing systems have several advantages over networks of fixed sensors, which are commonly seen already in commercial applications. They have the potential to observe areas where fixed sensors are impractical and can be more economical than a whole network of fixed sensors. However, one disadvantage they have is that they can take erratic paths around the room, leading to data coverage in each individual data collection period being uneven at best. There is a lot of work on interpolating data gathered at fixed locations or along pre-planned paths, but much less on data gathered opportunistically along erratic paths. When the path misses some areas of the room, how should we fill that in? That's the question I set out to answer. I evaluated potential algorithms to determine which one could accurately guess missing temperature values from measured values at other points in space and time. To measure the performance of different interpolation methods on sparse data, I used an indoor temperature data set gathered by what is essentially a robot vacuum cleaner with an additional light and temperature sensors added. You can see an image of the robot at the top of the method section of the poster. Working in one of the rooms at the U of O, the robot gathered temperature data in 2-hour intervals, resulting in roughly 30 separate collections of temperature measurements, which you can see in the right column of the poster. Along the top is the day of each collection, and along the side is the hour it was collected in the figure. To simulate the uneven coverage a mobile sensor might have, I redacted large areas of each collection, then used each interpolation method to try to predict what the redacted values were using the remaining information. You can see an example of this process in the second image in the method section of the poster, where the top left plot is what the original data collection looked like, and the top right plot is the redacted version that I give to each algorithm. Meanwhile, the bottom left and bottom right plots are the outputs of two of the interpolation methods given the redacted data. Finally, I measured each algorithm's performance by comparing their predicted values with the real values. I chose to apply this evaluation process to 4 different methods: k-nearest neighbors based interpolation, random forest based interpolation, using just the average of the collection, and using the average of the previous readings at the missing location. While definitely not exhaustive, there are some important contrasts between these methods. K-nearest neighbors and random forest are both machine learning methods, while both averaging methods are a lot simpler discrete methods. Additionally, 2 methods, random forest and location-based averaging, require training data from previous readings, while k-nearest neighbors and collection averaging only require partial data from the current collection period. As a result, I found that k-nearest neighbors, random forests, and collection and averaging methods were all able to outperform the time-based location average interpolation method. KNN, random forest, and collection average had average root mean square errors of 0.2, 0.266, and 0.245 respectively, versus the 0.688 for RMSE for location average. This makes sense intuitively for this data set, given that we're working with indoor temperature data, which tends to deviate less than other environment data like light, making nearby neighbors a more important predictor than past history. You can see additional evidence of this in the results of training the random forest model too. During the training process, the random forest model assigned large weights to the values of nearby points and extremely small weights to other features such as time and location, effectively degenerating to a model resembling k-nearest neighbors, even though it had access to other feature data. There are also a number of different directions that this research can go. Better interpolation of mobile sensing data can lead to anomaly detection inside of buildings. Additionally, as sensors become more prevalent on more devices, the need for better interpolation methods for sparse data will also grow. Finally, there is the possibility that parasitically collected environment data can lead to better calibrated real-world building models too.